Okay, so we are happy to have Ron Donagi from UPenn today, and he will speak about families of Hitchin systems and n=2 theories. Okay, so Ron, please.
It's a great pleasure to be with friends again. So I am going to go back and forth between this screen here where I can write and the paper where I can get to material a little faster. And I'm told that the audience is more mathematical than physical, so I'll try to take that into consideration and de-emphasize the physics. So let me start by reminding people what the Hitchin system is. So to start with the notion of a Higgs bundle. So that's V, which is a vector bundle, and phi, which is a global section of the endomorphisms of these values in something. So to be simple-minded, let's do this over a curve C. So there are various different definitions in higher dimensions. We'll just stick to the one-dimensional case. So C is a curve, genus G. V can be a vector bundle or a principal G bundle for some reductive group G. So G is GLN in the case of that corresponds to rank n vector bundles. Or G can be an orthogonal group, and that means that V is a bundle together with a quadratic form, and so on. And in any case, you take the endomorphisms of V, or I guess if you want to make it work in general, you call it the adjoint bundle of V, which amounts to the same thing. And tensor with K, where the basic case is that K is going to be the canonical bundle of the curve, holomorphic differential bundle. A variant is instead of the curve C, you take a curve together with an effective divisor D. So D is a bunch of points. And let's say that the points are distinct, so that D is a reduced divisor. So that's what's called the tame case. And then you replace K by K twisted by D. So instead of holomorphic differentials on the curve, you look at meromorphic differentials with poles on the specified divisor.
You are taking G as any reductive group.
Say that again, please.
Are you taking G to be any reductive group?
It is a reductive group, but without loss of generality, let's just take G to be GLN, and G as being essentially the vector bundle of rank n associated to G. So then you don't have to worry about too much group theory. Basically, all the results in the current work are in that case of type A or GLN. We are working on extending it to other cases, but it's going to be much more complicated. So let's just not worry about other groups. So there exists a Higgs moduli space. So you have to define a bunch of things. So you're looking at all pairs V and phi on a given curve C. So C is fixed. V and phi are the things that are varying in your moduli space. You have to define what you mean by an isomorphism of two such things. And as often in geometric invariant theory, you have a notion of stability or semi-stability. You have to throw out the really bad objects in order to have a decent quotient. So let's not worry about that. And what is important to us is that Higgs admits a map to a vector space B. It's the direct sum of cohomology groups on C of, let's call it L to the K, where L is this twisted bundle. What's the map? You send V and phi to the collection of traces of phi to the K. So phi is something that varies over the curve, and at each point it's a K-valued endomorphism or an L-valued endomorphism, some vector bundle. So raising it to some power and taking trace, you get a section of the kth power of L. You could do this for any K, but in the case of GLN, you go from K equals 1 to N. In the case of SLN, you go from 2 to N because the trace of the first power is already 0. And in general, the K's run over the degrees of invariance of G invariance. So for the orthogonal group, you get that all the odd powers vanish. You have only the even powers plus one more thing, which is the Pfaffian, the square root of the determinant, and so on. Again, we're going to work just with, or mostly with GLN, so that, or SLN, so that we'll take summation from K equals 1 or 2 going up to N, which is the rank of the group. And then in the case that there are no marked points, you make the right definition, you get that Higgs is...
Is it only me who doesn't see the bottom? Okay, yeah, okay. Now I see it, okay.
I'm more concerned that you'll be able to read the things that are displayed. Are those more or less legible?
Yeah, I mean, for me, yes, but I know a little bit of subject, so I can guess what is not clear, but maybe if somebody wants to ask a question or
by all means, it's a small group and
yeah, just unmute it. So.
I don't want to ask, but when you have this phi to the K, so do you regard the phi as an endomorphism on the non-bundle or?
Yes. So in the case of GLN, phi is just an endomorphism. Phi to the K, you just iterate it. For other groups, what you do is you take a group invariant polynomial and you apply that to phi. So that gives you a section of K to some power. That power is the degree of the invariant polynomial. So
And
again,
is this is for any Higgs bundle or just for the principal bundle you mentioned earlier?
so if you're working with an arbitrary group G, the only notion you have is that of a principal bundle. You don't really have a modular vector bundle. You get a vector bundle for each representation of the group. That can be, so you may as well just work with the modular of principal bundles. And there's a section of their adjoint valued in K.
I see. So V is fixed, but the field is changing.
The field?
The field of phi in the Higgs.
That's right.
In the top from Higgs to the B, the map.
So let me just make the next statement. I think that will make it a little clearer. Higgs is symplectic. For roughly speaking, Higgs is, so I'm writing this as a tilde rather than equality, the cotangent bundle of Bunn. So this is the moduli space of principal G bundles on the curve C.
Some stability, or it's a stack?
Yes, so that's why I don't have equality. I have a vague similarity. So there are different ways you can slice this. You can take Bunn to be the stack of all bundles. You take its cotangent bundle, and that'll give you the stack of all Higgs bundles. Or you can take the moduli space of stable Higgs bundles, and then this is no longer exactly an equality, because the notion of stability for a Higgs bundle is weaker than for a vector bundle. So you can have a pair V phi, which is stable, with the underlying V itself is not stable. And that makes things really interesting in places like geometric line lengths and so on, but it's not relevant to us today. So all you have to take away from this line is that Higgs is a richer object than Bunn. It has roughly twice the dimension. I mean, it has twice the dimension, roughly twice the content. So Higgs, ignoring the stability issue, a Higgs bundle is a bundle together with a Higgs field, which can be interpreted as a cotangent vector at V to the moduli of bundles. So altogether, you're getting the cotangent, and you have to be careful about stability, or else settle for the stack.
Okay, thank you.
Oh, okay, so in the case that D is empty, Higgs is symplectic. It's a cotangent bundle together, and the symplectic bundle, the symplectic structure is that of a cotangent bundle. Cotangent bundle to anything is symplectic. And the Hitchin map from Higgs to B is Lagrangian. So a point of B specifies a cover. So a point B in B gives a cover C tilde B of C. So in the case of GLN, this will be an n-sheeted cover. If you want to do it in a really clean way for all groups, for a general reductive group, this will be a Galois cover, where the Galois group is going to be the Weyl group of G. So if you're doing that version for GLN, you're getting cover not of degree n, but of degree n factorial, which is the order of the Weyl group. And you can go back and forth between this Galois thing called the camel cover and the speckle cover, which you get only for special cases. Anyway, a point in the base determine a curve C tilde, such that H inverse of B is, or maybe I should again say, is roughly equal to, because there are some issues of stability, the Jacobian of this curve C tilde B, or maybe more carefully, it will be the prime of C tilde B over C. So the kernel of the map from the Jacobian of C tilde B to the Jacobian of C, if you're doing SLN. For GLN, you just don't divide by C, you take the whole Jacobian. So it's an integrable, so it's an algebraically completely integrable system. You have a symplectic structure, a Lagrangian fibration. The fibers are abelian varieties. In fact, Jacobians are primes. You have a lot of control over them. And you have this the second structure, which is, and again, up to some modifications. There's also a different projection from Higgs to Bunn, which is also Lagrangian, but this time the fibers are vector space instead of abelian varieties. So in most of the literature,
And Ron, you said B is the base, right? In this set.
B is, yeah,
The B is also algebra.
I'm sorry?
B is also an algebra.
No, B is not an algebra. It's an affine space, non-canonically vector space.
It's a finite dimensional vector space. I'm taking a sum of a finite number of cohomology groups.
And that's okay. It's running up to M. Is that just arbitrary choosing or?
For G equals GLN.
Okay. Okay.
So most of the literature that I'm familiar with studies the Hitchin system on one particular curve. But some physics that I've run into suggest, and once it's suggested, it becomes a very natural question mathematically. So what happens as you vary C, the underlying Riemann surface? So we expect an object, let's call it curly Higgs, which lives over mg, I guess this one is just mg, the moduli of all curves. So I'm varying the curve C, I'm getting the moduli space mg. If I'm ambitious, I might want to go to the Deligne-Mumford compactification and allow some singular curves as well. This is supposed to be a fibration with the fiber of a given curve is the straight Higgs, the moduli space of all Higgs bundles on that given curve, and we fix the group once and for all. So what you'd expect is that there should be a base B like this, and the map will factor, where this horizontal map will put together all the Hitchin maps over the varying curve. B should be a vector bundle over the moduli space of curves. So above each point of the curve, over each point of the moduli space, meaning each fixed curve C, the fiber here will be a vector space, which is what I was calling straight B previously. And the fiber here will be the moduli space of Higgs bundles on that curve. And this map will be the Hitchin map. And hopefully it all fits together into a little diagram like that.
Is it kind of universal family?
Well, you would like it to be. Conjectures are cheap.
Hmm.
So let's think about that for just a moment. What do we want it to do? So ideally, script B should be a vector bundle over M bar.
Ron, can you move the paper up? Thank you.
Ideally, B should be a vector bundle. Higgs should be, I'm not sure what the terminology is, maybe relatively symplectic. In other words, you want to have a closed two form. Whoops, you want to have a closed two form on the total space of this Higgs, which on each fiber restricts a symplectic form. So that puts all the symplectic structures on the fibers together in some natural way. You'd also like to know that, if possible, the map from Higgs over B is proper. In other words, has compact fibers. So part of the beauty of Hitchin system is that indeed the fibers are compact. There are abelian varieties. There are Jacobians for GLN, there are prims for SLN. There's slight generalizations of prim varieties for any reductive group. So we have good control over them. However, I told you that every point of the base, every point little b in the base determine the spiral cover C tilde b. For generic point b in the base, C tilde is a smooth curve. So then we know what we mean by its Jacobian or its prime. But there will be a locus of points in the base called the discriminant, over which the spiral cover is itself singular. And that means that its Jacobian becomes non-compact. One of the periods goes to infinity. So the abelian variety of the torus acquires a non-compact direction. So if you just take the prim, it is not, this is non-compact. Nevertheless, the notion of stability that you use for Higgs gives you a compactification of this thing. So an important part of the Hitchin package is that the Hitchin map from Higgs to B is proper. All the fibers are compact, even for simple.
May I ask you, I mean, since kind of it's a wish, do you expect that other structures like non-abelian Hodge theory, they also extend to MGN bar in this universal way, that everything is universal?
Well, like I said, conjectures are cheap. So I haven't thought about this particular one in detail, but if we don't see a good reason for it to be false, then why not try it? I haven't really thought about it, so I'm not sure. So we'd like some sort of a package like this. So in fact, what the physicists like is not just naked curves, but curves together with punctures. So they want you to go back to this picture CD and extend that. So you'd like MGN to be the moduli space of curves of genus G with n distinct punctures. You'd like to go to MGN bar, which is the Deligne-Mumford compactification of that space. You'd like a B, which lives over that, which is the vector bundle, and a Higgs, which lives over both of them. In the punctured case, Hitchin space, or the moduli of Higgs bundles, is no longer symplectic. Instead, it has a Poisson structure. So it has a fibration by symplectic leaves. And the natural structure that puts them all together is called a Poisson structure. So whatever structure you have over a single curve, you'd like to try to extend it to the boundary. Well, let's say that this package is work in progress. We can do a fair amount of it, but the tricky part is to balance. There are two things pulling in different directions. Making it proper means you have to add a lot of stuff, so you don't have anything missing. On the other hand, keeping it symplectic or Poisson tends to ask you to be very careful to not add too much stuff, or else it will have to be symplectic. So there's a tug of war between those two directions. And that's why this is still a bit of work in progress. But basically, the result that we do have has to do with this part of the picture. So we can construct the Hitchin base over the Deligne-Mumford compactification in a way that makes it a vector bundle. So regardless of how degenerate the stable curve C is, we can define the base B in such a way that there's a natural candidate for what the fibers would be, but we haven't quite finished reconciling that part. So let me talk only about the right part of this diagram, this and that. Okay. So let me switch. I'd like to go through a few items from the introduction to the paper. Is this visible now?
Yeah, it's visible, and it's in the archive. Yeah, just for people who do not know.
Yeah. Let me go to the top. This is the paper, Families of Hitchin Systems and Encoded Theories. I awfully neglected to mention this is all joint work with Aswin, Balasubramanian, and Jacques Distler. I did say that in the abstract. And here's the archive number, 2008, 01, it's not 2008, it's 2020, August, 01021. Oops, what did I do? All right. So allow me to read a few items, mostly from the introduction. So as I said, this comes out of physics. The context is called superconformal theories. The four-dimensional theories have been around for a long time. And Seiberg and Witten taught us that behind them, or behind the Coulomb branches, there are integrable systems. And in many, so those are often referred to as Seiberg-Witten integrable systems. And the case that I want to talk about is where the Seiberg-Witten integrable system is essentially the Hitchin system, or a particular case. So a particular class of supersymmetric theories that admit a uniform geometric construction from 6 dimensions receive greater attention. Those are called theories of class S. So you start with a 6-dimensional superconformal theory. You compactify to the dimensions. So the thing that you compactify on is going to be a Riemann surface. That would be the thing that I've been calling C. And you end up with a theory where the Seiberg-Witten integrable system is going to be essentially the Hitchin system for that curve. The group is built into the theory, and then when you choose a curve, you compactify on it. So this theory comes with a bunch of parameters corresponding to the moduli space of curves. And in fact, the physicists do like very much to go to the boundary. So that's why it's important to do things not just over the moduli of curves, but over the Deligne-Mumford compactification of the moduli. So in this realization, starting from 6 dimensions, the Hitchin system, which I've already explained, plays an important role, namely the Coulomb branch, which I'll just take as a black box coming from the physics, can be described as the base B of the Hitchin system, which I described for you before. You can also compactify, instead of to 4 dimensions, you can compactify further to 3 dimensions. Basically, you compactify the Riemann surface across a circle. In modulo a few things where I'm going to be slightly inaccurate. When you do that, instead of the Hitchin base, you get the entire Hitchin integrable system. So both the Hitchin system and the base of the Hitchin system arise as moduli spaces of compactifications of these superconformal theories from 6 dimensions to either 4 or 3 dimensions.
Do you have to have at least one marked point for that, or your discussion with MG also can be applied? Do you have to have defects in the theory? Or
the answer. I might need at least 1 point. I'm certainly going to assume that I have the points. So yeah, I think you do need to assume some points. So the general setup is that you have some points where the theory has some defects, and those points become the punctures, or the divisor D, along which the Higgs field acquires singularities. There's a big discussion here about one of the reasons that GLN is much simpler than the other groups. I'm not going to worry about that for now. But what I want to point out is that what the superconformal field theory sees is meromorphic Higgs fields with poles on the given divisor D. If you don't say anything further, you get a Poisson structure. If you want to describe one symplectic leaf of that Poisson structure, you need to fix the conjugacy class at each of the punctures. So that is the conjugacy class of the residue of the Higgs field. Higgs field is meromorphic, it's first order pole. So its residue is just an endomorphism. So it's an element of the Lie algebra. And you want that to be in a given conjugacy class. In fact,
and you will fix it, yeah?
Yeah, and in fact, in order for this to give you a superconformal field theory, the conjugacy class needs to be nilpotent. So there's a conjugacy class in the Lie algebra, and it needs to be nilpotent. So it's not zero, but it's nilpotent. So in the case of GLN, we know how to describe nilpotent orbits. They're given by partitions of n. So the conjugacy class is simply described by the Jordan blocks. So you take the number n, you take a partition into bits. Let me see if I can do this here. So you have some partition of n. And that tells you that you have a 5 by 5 Jordan block followed by two 1 by 1 Jordan blocks. So you call that the Hitchin orbit or the Hitchin partition that describes this particular symplectic leaf of the integrable system. The dual partition, which in this case will look like something like this. It's called the NAM partition. So all I did was I transposed the previous one, turning rows into columns. But so if this is the partition 5, 1, 1, this is going to be the partition 3, 1, 1, 1, 1. So it's a different partition of the same number. For general groups, it turns out that the NAM partition is the right thing to look at rather than the Hitchin partition. In the case of GLN, they determine each other. In the case of other groups, there can be several different NAM partitions that give you the same Hitchin partition. So there's some loss of information for other groups. And that's what I'm trying to explain here, but never mind that. Okay. Oh, how do I get out of here? All right. So the reason that you want to look at the compactification is because the boundary where you let the period tau go to infinity, so the plumbing fixture, some local coordinate q goes to 0, gives you a boundary component of the moduli space, and that's where some part of the gauge group becomes weak or weakly coupled. You can, instead of going to divisors, you can go to intersections of divisors. In fact, you can go all the way to the smallest strata, which is just isolated points. So those are intersections of 3d minus 3 plus n boundary divisors. They correspond to pair of pan decompositions of the Riemann surface. And each of those gives you a presentation of the family formal field theories as a gauge theory. So physicists like that. The actual group that you get is part of why this paper was written. The expectation is that your group is the group that you started with. But I'm going to show you some examples. I hope I have time to show you examples where the group that you get is actually a proper subgroup of what it could be. So you might start with GLN and end up with a symplectic subgroup or a unitary subgroup of lower rank inside it. So what that means, so that should translate into some identities on hyperkähler quotients. So the moduli space I'm describing are called Coulomb branches, and there's a duality between Coulomb branches and Higgs branches. And usually this is done in the language of Higgs branches, which are described as hyperkähler quotients, the product of Higgs branches of the individual theory. So you have an individual superconformal field theory for each of the 2G minus 2 plus n components of the pair of pan composition, divided by a product of simple factors, one at each of the nodes. There's 3G minus 3 plus n nodes of the pair of pan composition. If you start with, I don't know why we call it J. This J is what I was calling the group G. And the point is that in specific cases, we don't get the full group, we get a proper subgroup of this G to the power. And that tells you that you get, so if you look at different pair of pan decompositions of the same Riemann surface, you get different ways of describing the Higgs branch, which in particular give you identities between different hyperkähler quotients, which as far as we can tell, cannot really be proved in any other way. All right. So the other bit of physics here is the cowboy folklore. So the reference is Sergio Leone, Il Buono, Il Pluto, Il Cattivo, or The Good, the Bad, and the Ugly, which was taken out by Gayotto and Razamat, and also earlier by Gayotto and Witten, one of them in the 4-dimensional case, the other in the 3-dimensional case. They didn't mean to do that either. All right. So you say that the theory is bad if these line bundles LK. So LK is basically the thing that I was calling K, was posing D, raised to the power K. You have to correct it a bit because we are taking section of that which at each of the points lies in a particular adjoint orbit. Putting it in an adjoint orbit might lower the order allowed for the pole, and I'll give you a couple of examples in a minute. So LK is the line bundle in which the line bundle whose sections give you the Hitchin base, basically.
So it depends on the partition.
So it depends on the partition. That's right. So from now on, our input is a group G, a curve C, which could be singular, a divisor D on the curve, and at each point of the divisor, we specify a nilpotent adjoint orbit, which in the case of GLN just means we specify a partition of the number n at each point. So that's our input package. if the Young diagram is one row, which means that the Hitchin orbit is just a single Jordan block, that's called a regular nilpotent, then LK is going to be K with poison D raised to the kth power, and you subtract 1 at each of the points. Subtracting 1 from the traces of the powers of phi is equivalent to making phi a nilpotent, and you don't want anything further. But if your Young diagram is a different one, which corresponds to a smaller orbit at the closure of the regular one, then you want then your LK will consist of things that have a pole for the K, but also more than 1 0 in order to force it into the smaller orbit. And there are detailed algorithms that give you the translation between the partition and the orders of vanishing or the orders of poles. Did I answer your question? Yeah.
Yeah, at least the immediate question. Maybe I'll have more. Yeah.
Anyway, so we have these line bundles LK.
I see.
Determined
The LK here, they are all irrelevant. Earlier I thought the L upper K was the tensor product of the non-bundle K times.
Yeah.
But
So,
this is not. This is just to say, with several non-bundles only.
No, it's corrected. It's a little bit twisted. This KC of D in the tensor power K.
That is the tensor power, right?
Here's LK. LK is canonical bundle with poles on D, raised to the power K.
Okay. Yeah, I was correct.
Minus, from correction, summation over I. D is P1 plus, D is going to be summation PI. I just indicate which point we take. Summation over I of the point PI with some multiplicity, which I will call chi-I-K. Chi-K is some integer which specifies which orbit we're in. So if this is your Dinkin diagram, then always are 1.
Young diagram.
This is your Dinkin diagram. That means that all your Jordan blocks are 1 by 1 with eigenvalue 0. That means that the residue is actually identically 0. That means there is no pole. Then chi-I-K is K. And for a diagram somewhere in between, there's a formula for chi-I. In terms of the partition, you can specify some number between 1 and K, which is the order to which having a residue in this conjugacy class forces the section to vanish. Anyway, we say that the system is bad if for some K, there's a higher cohomology. So that tells you that the dimension of the base B is not what you expect. What you expect is that the dimension of the base, which is the sum of H naughts, you'd expect the higher cohomology to vanish, so H naught is the Euler characteristic, so the degree minus genus plus 1. So there's a natural formula for what the dimension of B should be. And you say that theory is bad if there's some H1, which means that the dimension of the base is bigger than what you expect. Then the physicists define 2 other types of theory, which are ugly and good. And this is a trichotomy. Every theory is bad or ugly or good. For us, it turns out that ugly and good, the distinction between them doesn't make a huge difference for us. So we just come up with a new terminology. We say that the theory is okay if it's not bad, meaning if it's either ugly or good. And I'll skip the distinction between those two. And just to check the credentials, J. Sturgis, gunfight at the OK Corral, Paramount Pictures, 1957. So we have good, bad, and ugly, and okay.
So then mathematically it's a property of the whole of all the data of the Hitchin system and the nilpotent orbit. Yeah, so
Definitely. Always, yeah, definitely. So it's basically a property of a symplectic leaf of the Hitchin system. That's what the nilpotent orbit specifies. All right, so how much more time do I have?
well, how much time do you need? Our kind of, it's not rigid. You can go over the time.
Oh, 3 more hours?
It's a Zoom talk, so people who are kind of have to leave, they can leave. But those who wish to listen, they can stay. So it's one advantage of this time.
All right. Well, I'll try not to use all the next 3 hours, but I might go for a few minutes beyond.
That's okay.
Are you seeing the paper or the paper, or the handwritten version or the printed version?
Currently, it's the paper under section 5.
Thank you. So actually, let me show you the global story. So the claim is that if you take the LKs, which I defined previously, let's start with considering genus 0. So that's technically a little simpler because in genus 0, all nodes are separating. They break into separate components rather than just being a node on a particular component, which is possible in higher genus. So you can label the components of the boundary by subsets of the divisor D, which is P1 through Pn. And for stability, you need S to contain at least 2 points, and its complement, S check, to contain at least 2 points. And then at point of this boundary divisor, the curve C splits into 2 irreducible components, CS and CS check, or C left and C right, such that the points that are in the subset S move to component CS, and the points that are in the complement move to C complement. So so I've described this line bundle LK. It's the Hitchin line bundle of the universal curve. So script C is going to be the universal curve over the moduli space. So it's the family over MG bar of MGN bar of the corresponding curves. So you can take the global sections of LK, or rather take the line bundle LK on C bar and push it down to MG bar. That means you take homology along the curve fibers, or global sections along the curve fibers. So by general nonsense, you know that that's going to give you a torsion-free sheath over the moduli space. And then you take the direct sum of those over all K, and that gives you one possible version of the Hitchin base. The problem is that this one is not locally free. It's not a vector bundle. It's only torsion-free. In order to make it torsion-free, we need to modify L, replace it by a smaller line bundle, L prime. So L prime K is LK with a vanishing of a certain crazy order on CS. So C sub S is going to be the divisor in script C bar corresponding to S. So remember, script C is the universal curve. Script C bar is the universal curve over the compactified moduli space. S determines a locus, so it gives a divisor in MG bar where the curve splits into an S component and a complement component. So take the S side, the S component, take the union of those over all points of that divisor. That gives me the divisor that I'll call script C sub S. So it's a divisor in the universal curve corresponding to CS. It lives over the locus where the curve splits according to S and S complement, and it picks out the left component rather than the right component. So then you take this crazy formula, formula 85. For each point I, and we're fixing a K, chi Ki was the order of vanishing. So K minus that, that's the order of pole, right? Because we took meromorphic divisors, meromorphic one forms, this first order pole in D, raise it to the power K, so we allow the Kth order pole, but then we're imposing chi I K zeros. So the difference is the remaining order of pole that we're allowing. And you do K minus 1 minus the sum of that of all points. So it's not immediately obvious why that's the right thing, but that, or rather the maximum of that is 0, turns out to be the right multiplicity, NSK. So our theorem says that if we modify the line bundles L by this particular combination of the boundary components, then over the interior, we haven't done anything. So we get the same Hitchin base over the interior, but it now allows us to extend it to a vector bundle rather than to a free sheaf over the bound or over the compactified space. And it has a generalization to higher genus. Like I said, genus 0 is just for convenience of explanation. The only new term is this one here. You subtract the genus of component CS multiplied by 2K minus 1.
So I'm a bit confused. Over the interior, you should have not just a meromorphic Higgs bundle, but a meromorphic Higgs bundle with residues in some nilpotent orbits.
That's right.
Which means that they are not just sections of this twisted, of the tensor power of the twisted canonical class, but there are some other conditions, yeah, on the residues.
Chi Ki. So knowing the orders of vanishing for all K is equivalent to knowing the partition through some algorithm that I showed you exists, but I didn't write it down.
It's a question. No. It's a question of what do you extend to the boundary. You extend to the boundary a meromorphic bundle or meromorphic Higgs bundle or meromorphic Higgs bundles with residues which belong to particular nilpotent orbits, and the whole structure extends.
So if you remember, I told you what the ideal theorem would be, and then I told you that I'm not ready to prove it. So the ideal theorem would discuss the correct notion of a Higgs bundle over a degenerate curve. And we'll describe the whole Hitchin system. What we have at this point is the base of the Hitchin system. So we're not describing the Higgs bundles over it. We're just describing what the modular invariance will be.
Okay. So you prove that the family of bases, Hitchin bases, form whatever universal Hitchin base. Yeah, that's what you.
That's what we're willing to claim at this point, or that's what's proved in this paper.
Okay.
And we're working on extending that to a family of symplectic integrable system over the entire Deligne-Mumford shebang. But that's working.
Okay.
Okay.
Mm-hmm.
So the theorem says that the family of Hitchin bases script B, defined with the L prime K's, is a vector bundle over MG bar N. So the point is that this makes a correction only when one of the H1s is positive. Okay. Let me switch to the handwritten version. All right. So, example, let's look at M04 bar. So we're taking genus 0, 4 marked points, as I think everybody knows. This is just CP1, it's one-dimensional. M04 is P1 minus 3 points. The bar adds the 3 missing points, gives you a compactification P1. You remove 0 and infinity, that's M04 without the bar. So given 4 points on P1, they have a cross ratio, which is not 0, 1, and infinity. And when you compactify it, you just allow 0, 1, and infinity. Okay, so what do we get? So let's say we're doing SL4. So we're getting that B is going to be the direct sum of B2, B3, and B4. Well, B2 comes from quadratic differentials, B3 from cubic differentials, and B4 from quartic differentials on the curve. Since it's SL4, I don't worry about B1. So script B is going to be a vector bundle over P1. We know that it will decompose into 3 pieces of bits. But in fact, you know that any vector bundle on P1 decomposes all the way into a sum of line bundles. So what are these? So we compute and we show that, let me make sure I get the right answers. B2 is a rank 1 bundle. It's just O of 1. So the bundle that you're taking is canonical bundle with poles of 3 points. That doesn't sound right. Poles at 4 points. So if you take the quadratic differentials, so that section is of minus 4. At each of the points, you would like to put a second order pole, but making a nilpotent says that the top residues vanishes, so you're only allowed a first order pole each. So this is quadratic differential with a first order pole at the 4 points. That's the same as the trivial bundle on your curve. So it has a one-dimensional space of section. So that's why you get a line bundle. The question is, what is that line bundle globally? And you compute it, and it turns out to be O of 1. And similarly, B3 turns out to be 3 copies of O of 1. But B4 turns out to be 4 copies of O of 1 plus 1 copy of O of 2. Let me just make sure that I got that right. I did. So that says that this decomposition here as a God-given refinement. B2 and B3 cannot be refined, but B4 as a natural piece that comes from the O1s and a residual piece that comes from the O2. So that says that given any curve of genus 0 with 4 marked points in the quadratic differential zone, you can you have a fine structure. You can decompose the space of those into a 4-dimensional piece and a remaining 1-dimensional piece. What is that? What does that tell you about the moduli space? We don't understand that, but it's got to give some information. And of course, this becomes richer and richer as you go to higher and higher orders. So the next piece will be 401 plus 302. The next piece will be 401 plus 402 plus 1 copy of 03, and so on. So the number of pieces keeps increasing. All right. So I'm going to skip the example. So we have a large number of concrete examples, all done with P1 was 4 points. Let me just show you a typical one. So here is P1 that is split into 2 components. Each of them is a rational curve. They meet in 1 point. Let's say the partition on the total points is 4, while the others it's 3, 1, 2, 1 squared, and so on. So we compute each of these cases and analyze what happens. The basic phenomenon is that you have pieces in the Hitchins that come from the left curve. You have other pieces that come from the right curve. And then you have central pieces which are supported at the node. The image of the restriction or the residue map at the node itself. And the central nodes have an interpretation as the Casimirs of this group H, which I promised you previously. So there's often, the physics often sees a reduction of the structure group from G, which for us would be GL4, I guess, in this case, or GLN in this case, to some proper subgroup H. And you determine that subgroup by counting its Casimirs. They're given by the part of the invariance which is supported right at the node. So we do various examples where we show what the group is. So I think the 5th example is probably the most interesting one. So here's an example with SL4. So K can be 2 or 3 or 4 for each of these cases. Here are the left parameters, here are the right parameters, here are the center parameters. So the fact that you get a quadratic Casimir and no cubical quartic tells you that the weak group that you get is SL2 rather than SL4. Okay. I wanted to show you 2 more things before I finish. One is an agricultural procedure for proving the theorem that says that you get a vector bundle. The idea is this. Consider a curve C, which is nodal and
Roland, do you want to switch the screen, because we are seeing the paper, not your computer screen.
Oh my God. Oh, so you missed all my pictures of the examples.
Yes,
Well,
yes, we did.
I humbly apologize.
No, we should apologize because we should have told you earlier. This is the bad side of the Zoom talk, and participants, we should respond to the speaker.
I simply opened the paper, and so I just follow what you were saying.
So I wanted to say a few words about how the main theorem is proved. So let's say you have a curve C, which is nodal, with various irreducible components today. Each of them has genus G, and let T be the number of nodes. Now you can see my page.
Yeah, it's visible.
So T is the number of branches of nodes. So that means if the node is strictly on the curve intersects itself, you count it as 2. If this component intersects another component, you count it just as 1 branch. And you choose a set S of marked points, one for each component. We say that the component is blighted. If its genus is 0, it meets the rest of the curve in only 1 point, and there's a numerical condition that the sum of the orders of the poles at the selected points is bounded by k-1. And then we define this number NA, which ends up being essentially the correction that we needed to go from the L to the L primes. And the first lemma says that let's skip that. Let's just look at the second lemma. If C has no blighted components, then L prime is LK, the correction vanishes, and H1 is 0. So the way we prove that the whole thing is a vector bundle is as follows. We start with some curve, and you say if it does not have any blighted components, then H1 is 0. We're good. That means that by standard theorems about direct images, we have a vector bundle. If we do have a blighted component, we're going to prune it. So we describe a procedure for pruning the blighted components. So assuming that you do have a blighted component, so it intersects the rest of the curve in just one node P. The pruning operation consists of removing the extra component CA and replacing the branch of the node on the complement by the marked point, and you specify chi k to be 1 plus that number NAK that we calculate. And the rest of the proof basically shows that everything is consistent. So the upshot is that the line bundle L prime K twisted by the point on C check is exactly the line bundle that you would construct by the previous recipe on the curves before the pruning. So eventually you arrive at the curve with no blighted components, and then you apply lemma 2 to that and conclude that H1 is 0. So that shows that L prime, which is the corrected version of the Hitchin bundle L, has no higher cohomology ever. So that says that if direct image is locally free, that's how we get the vector bundle. Okay. Well, I was hoping to say a few words about the relation between our theory, especially the notion of the OK bundles, and Deligne-Simpson question about representations of fundamental groups, but I'm already past time, so let me pass that to another opportunity.
Okay, thank you very much. Are there any questions? So you can unmute yourself if you would like to ask a question, and just go ahead. Okay, maybe people are still thinking, so let me ask you a question. So when you mentioned Deligne-Simpson, do you mean with nilpotent residues only? Deligne-Simpson problem is to find like bundle whatever. By the way, with any group or with just with GLN, Deligne-Simpson, with general group or with
Well, as you know, we promise a lot more than we deliver. We'd like to do things for an arbitrary group, but at the moment, in this paper, we only deal with SLN. So I like.
Okay, but I mean, you expect that the technique can be generalized to, but do you mean to consider, I mean, only nilpotent residues? Because all what you mentioned is just nilpotent, no eigenvalues. Somehow I was confused. Because you extend basis of Hitchin systems to the boundary, which consists of spectral curves. But in fact, your residues are only nilpotent, so somehow it's a bit...
The residues are nilpotent, because at points other than the divisor D, there's no nilpotent, you get all sections. So the story does extend to all residues, not non-nilpotent residues. The restriction to nilpotence is just because that's what's relevant for the physics. They want superconformal field theories. They only get those from the nilpotent classes. So the right notion in general is that of a sheet. So let me explain what a sheet is in the Lie algebra. So you give yourself a Lie algebra. You fix a dimension. You look at all adjoint orbits of that dimension. You take the unit. That's
if you are thinking, if you are writing something, I don't see it. But
that's right.
You just say, yeah.
I mean, if you want, I can write it. But
no.
Now
So far, it's fine.
So you're in a Lie algebra. You take the union of all orbits of a given dimension. You take a connected component of that. So an irreducible component of that. Okay, that's called a sheet.
Okay, Lisa is asking, how do you spell it?
So you're talking about nilpotent orbit.
Should, yeah, that's, yeah, okay, good. I mean, it's just a term, Lisa, whatever. Like bad, good, and ugly, whatever.
Well, but this one is actually about mathematical. It goes back to the work of Bala and Carter on representations of these groups. So this one does not come from the physics. This has been in the math literature for 30 or 40 years now.
All right. Anyway, you take a component of the union of orbits of the same dimension. That's not necessarily nilpotent, just.
So if you start with the regular nilpotent, that means a single Jordan block, nilpotent on the diagonal. The sheet consists of all regular orbits, meaning all orbits whose centralizer has the smallest possible codimension, which is the rank of the group. So those are the natural directions in which you can deform the nilpotent without in a flat way, without jumping in dimension. There are other deformations that you can imagine, but they're not going to be good. So the theory, so the story that's stated for the nilpotence has a natural extension to one sheet at a time. So like you can do it for all regulars of all minimals and so on. And the directions away from the nilpotent are interpreted as mass parameters. So the conformal theory is a massless theory, or you want all the masses to be zero. The deformation directions give you massive theories.
But then if you have non-zero eigenvalues, what do you require when you approach the boundary? I mean, it's kind of, I always feel uneasy when you have, when it's not nilpotent. You're answering Lisa's question. Yeah.
I didn't make up the name. I think it was either
Yeah,
Richardson or invented it a long time ago. And it plays a role in.
no, I mean, I'm asking because in this Deligne story business, if I remember correctly what my son told me, that there is a difference between, for example, closed conjugacy classes and non-closed. And the closed, like regular semi-simple, not nilpotent, they are much easier to handle.
Mm-hmm.
And so...
Well, there are very, very few closed classes. The only closed class is the zero class.
In the nilpotent world, yes.
Nilpotent,
I asked you whether you allow eigenvalues of the residues to be non-zero, non-nilpotent case. I understood that you could, no? Or at least you expect. This nilpotency condition, you told me that it motivated by physics, that you need some conformal, that the theory is conformal or something like that. No masses. Yeah. But in general, what if mathematically I do not see why you cannot have non-nilpotent residues,
Yeah,
especially...
mathematically I don't think.
Huh?
Yeah, mathematically I don't think you need that restriction.
Yeah.
I may take my back in a minute, but I think you can. I think basically what you get is that the results for an nilpotent class work the same for any non-nilpotent orbit in the same sheet. So as long as you're deforming in an equidimensional way,
Mm-hmm.
Mm-hmm.
you should get the same result.
So then you use Jordan-Chevalier decomposition. You separate the semi-simple part and the nilpotent parts.
I see it's the opposite. You just combine all the orbits of the same dimension, and so if you have kind of one representative in with non-zero eigenvalues, you can add a nilpotent matrix to it without changing the dimension or something. Yeah, okay. I have also another question. Ron, you spoke about tame case, like poles of order 1. What prevents you to do the wild with a regular Higgs?
Well, that's yet another future paper, I suppose.
Yeah, it's a question who will write it. No, my question is, what are these in the tame case? You have only discrete invariants, which are these partitions for GLN. Yeah, nilpotent orbit of GLN is determined entirely by this partition, if you consider nilpotent residue. Now, in the regular case, do you have some continuous parameters? Because the group is no...
I never really learned that as I should, but you know, you have Stokes phenomena and all these things.
No. It's not Stokes phenomenon. It's on. It's. I have the right to ask you because you wrote a paper with Diaconescu and Pantev on the regular case. So then, yeah. So in that case, you might have. Irregular Higgs bundle, but with residues which have nilpotent coefficients or something like that, like nilpotent matrix divided by Z in Z square, DZ or DZ square, something like that. And so then you should look for the orbit of such a thing, but it's not just GLN. It's something like GLN over truncated polynomials, something like that. The group is different, so this way I'm kind of confused whether it's that easy.
Yeah, what I remember, it becomes very complicated.
It's too okay.
Which is
So,
not much help.
sorry. Yeah. All right. Okay. Maybe
So, yeah,
people.
I'd love to. Yeah. Let me
And
also
also,
apologize that.
No. But also maybe my last question. From the point of view of the spectral correspondence, when you want to treat not just basis of Higgs Hitchin system, but Higgs bundles together, I mean, you consider kind of spectral curves with whatever, like line bundles in the smooth case, and you can vary this. This gives you some piece of the moduli space of Higgs bundles of the fixed curve, and you also vary curve itself. Yeah, so like, and so you want to kind of degenerate this to go to the boundary. Now, in this story, you have a three-dimensional Calabi-Yau, about which you also wrote paper long ago with the same people. And so it looks like these two types of deformations are just different pieces on the moduli of complex structures of this single. I mean, is it kind of upgraded to more general, like three-dimensional Calabi-Yau, or maybe some physics give you a hint of what should expect?
Well, sadly, the dictionary between spiral curves and Calabi-Yau threefolds seems to suffer from all kinds of problems when you start putting punctures in.
But
so there really isn't a very, in the punctured case. So you and Kontsevich looked at the case of GLN.
Yeah, but let's
work.
just GLN and you also with Emanuele. And
that's right. We also tried that, and I now have some students working on special cases of that, but it doesn't seem like we have a really good, clean story in general. Point well taken. We should check to see when we do these degenerations of the curve, what does it correspond to in terms of the threefold? My guess is that will have to wait until after we've extended the theorem to the one that I want rather than the one I have. Because right now we only have information about the base. We really need information about the Hitchin system before we can say that the Hitchin system matches a Calabi-Yau integral system.
And so this 3D point of view doesn't help you to extend your theorem from the base to Higgs bundles. Somehow you're talking about.
So you think it'll be on the curve?
Yeah, I mean, you have kind of just one Calabi-Yau and different directions in the moduli space of complex structures. You can deform your curve, base curve, which normally people don't do. It's kind of your new idea. And you can deform the spectral curve itself, which people often do, but it's kind of, it looks like you move in the moduli space of complex structures of a non-compact Calabi-Yau threefold, something like that. Yeah. I think Emanuele wrote after irregular paper, three of you, he wrote some paper without you and Tony, where he degenerated, if I'm not mistaken, he degenerated the curves. Anyway, he considered some degenerations of the Calabi-Yau to the boundary of the moduli space. And he made computations about this partition function, which kind of gave you, well, whatever this generating, it's Haussel and others formula. I think he did it, but since he is not here, so we cannot ask him to confirm or to kind of disprove what I'm saying.
Gotcha.
So anyway, more questions, because it looks like I kind of occupied the speaker. More questions from the audience. Okay, people are that impressed that they have no questions. Probably they just started to read your paper. It's actually very interesting. I mean, it's kind of...
Either it was exceedingly clear or exceedingly murky.
Well, it doesn't matter if it kind of raises, it sparks the interest, it doesn't matter because it's very clear or the other way around. The main thing is to get people to be interested in and read the paper, which I will certainly.
So I hope it comes across a lot of questions that remain open. And I think at least some of them are reasonably interesting.
Yeah, but okay. All right, if there are no questions, so thank you, Ron, for a very interesting talk. Thank you very much.
Thank you very much for the...
Yeah, and yes. And so then this is it.